Great. So I guess because we are close to the end of the semester, Tom and I thought that today, rather than being very specific about the topic, we'll give a bit of a bigger picture about current interesting research in machine learning. And of course, since you are taking this class, by now you already know that machine learning is this amazing research field. But it's not only intellectually stimulating, but also has changed the world and had amazing impact in many application areas, ranging from, say, speech recognition to information retrieval to computational biology and so on. I mean, basically, all areas of science and computer science have benefited and invest significantly because of machine learning, right? And this is something that people widely recognize today, like in industry and academia. Okay, so machine learning has changed the world. But I also think, and I guess Tom thinks so, and many of us think so, that machine learning has changed the world, but the world is changing machine learning too. Okay, and in particular, the wide variety of new types of applications and the explosion of data have really forced machine learning to very quickly evolve and significantly expand its basic set of tools and approaches. Okay, so some of the tools that we've talked about in our class are very basic tools. But there is a lot of exciting activity in machine learning that goes beyond those basic tools. And this is where the current research is and what's needed for the next generation. Okay, and just to give a couple of concrete examples. So, I mean, this is something that we've implicitly talked about throughout the course. So, for example, most of the techniques we talked about in the course assume that humans can label or annotate all the data available for training, right? But most modern machine learning applications have such massive amounts of data that it's hopeless to have humans annotate it all, right? Like, for example, there is brain imaging data, massive amount of data, like coming from surveillance data, lots of data for information extraction and computational biology and so on. So it's hopeless to have humans annotate it all. And I think one of the cool directions in machine learning these days, and a little bit talked about that, is to design learning techniques that somehow most effectively utilize the available data, but minimize the need for expert or human intervention. Okay, and we've seen in the course some techniques related to semi-supervised learning and active learning, but these are just very stylized approaches, and there is a lot of exciting activity on doing this even better. Right, so it's one new key challenge, or more modern challenge, to design techniques that most effectively utilize the available data, huge amounts of data, while minimizing the need for expert intervention. Okay, it's a real issue today. It wasn't such an issue 20 years ago. Okay. Now, as a different example of a modern challenge, so in some of the modern machine learning applications, we have massive amounts of data distributed across multiple sites or locations. So, for example, we could have large amounts of scientific data or large collections of video or image data, right? And in such cases, in order to do learning over the combined data sets, the holders must communicate, right? And so, for example, in this context, communication becomes a new resource. So in addition to human labeling effort and computation, which are the two key resources we've been talking about throughout the course, now we also have communication as a key new resource, okay? And this just interactive learning or learning algorithms that most effectively utilize the available data, and also distributed learning, these are just examples of modern machine learning approaches that are widely researched these days. But there are many more, and for example, Tom talked about some of them, like never-ending learning and deep learning. There are other issues like multitask, transfer learning, or somehow we want to leverage data from many related tasks to learn more efficiently new tasks, and so on. I think Tom will talk about that a little bit. Right, so there are many exciting new approaches that go beyond the classic paradigms we've been talking throughout the course. And one thing that I find particularly interesting is that each of these approaches brings up a new set of challenges and resource constraints, that we have to worry about, resources and constraints that we have to worry about. Right, so classically, the two constraints we would think about are computation and the amount of data, potentially labeled data, right? But now suddenly we have to think about many more resources and constraints. So for example, we have to minimize human labeling effort when we do interactive learning. We have to take into account communication efficiency when we do distributed learning. Or actually, we have to also think about privacy when the data belongs to someone, right? So some of the machine learning applications involve sensitive data, right? Like medical data or genomic sequence data, and privacy becomes a key constraint or resource that we have to really worry about, okay? Or even, so privacy, but even incentives in cases where the data actually belongs to someone, like some research groups, or say Google or Microsoft, right? So what incentive would they have to share with us the data? And what type of data? Okay, so suddenly we have a lot more resources and constraints that we have to think about compared to the classic machine learning status 10 years ago. Okay, so it's very exciting. And this is, I think, what happens currently. Okay, so this is kind of a current picture. And of course, there are issues of scalability, right? I mean, even for the classic constraints like, say, computation, there are many issues regarding scalability and so on. But I mean, this is really, I think, a picture of the current machine learning. And I guess at the end of the lecture, we'll talk more about the future machine learning. But even the current machine learning was very different from machine learning 10 years ago. So lots of exciting topics. Okay, and I think Tom will touch on, so he already started last time to touch on deep networks, so we'll continue, or 2 lectures ago, he'll continue with deep networks, then I'll talk a little bit about privacy, and then each of us will talk a little bit about the future of machine learning. Yeah?
Sure.
So if you have more comments about this too.
I agree.
Good, excellent comment.
So what we're trying to do here, is have an open discussion about. Oh, should
That's
I
a good point. Yeah, that's a good point.
Sure. We're trying to do here is have a discussion about some themes that we see as being increasingly important in machine learning over time. And we agreed that we would each pick one and talk about it for 10 or 15 minutes. But then we would open it up to a panel discussion among a collection of experts who haven't arrived yet, but will be here soon. And have just kind of a brainstorming discussion about what are some of the directions in machine learning that we believe will be increasingly important and good research topics now and important applications in time. So given that we both got to choose one to talk about for 10 or 15 minutes, I chose this one. It seems to me this is, the whole theme of deep learning is one of the most important current developments in the field. So already it's having applications in commercial enterprises of many types. And so I want to take my 10 to 15 minutes, I'm looking at the clock, to make 2 points. We talked about neural nets last week. And I want to make 2 additional points here today. So last time we talked about neural nets, we pointed out that one of the key things in deep neural networks is that they have many stages of hidden units that they go through to compute their results. And we also talked about the idea that a lot of the training and what makes deep networks valuable is that they're trained to produce as output the same thing you give them as input, with the idea that this is a way of forcing the network to come up with, in the middle, a very interesting and intricate code to capture the distribution of inputs that you give it. And learning that representation is actually one of the key reasons why deep networks are important. So, and we talked about, this is a slide from the other lecture, we talked about how we could train these, for example, by, in this paper, by training just one stage at a time and then concatenating them, putting them all together and training again. But we didn't get to look at, here, for example, is an example of how those learned representations can look. So here's an example in one slide of a deep network that's trained to do image representation and also image classification later. this is a kind of state-of-the-art network. So as you can see, it's trained on 10 million unlabeled images sampled from YouTube. The network is trained to produce the same image as output that it got as input. It goes through, the training is very expensive. It took 1,000 machines and 16,000 cores over a week. So we're not talking about running on the laptop anymore. And actually a big industry here on the side is figuring out how to use GPUs for speeding up the processing of this training. The network itself has 3 multi-stage layers. Each stage itself is a 3-layer network with a particular specialized architecture. Over 1 billion weights parameters trained in the network overall. And it dramatically increased the state-of-the-art results for classification accuracy of 1 out of 20,000 image classification problem. If you look at one of those features that's learned in the middle of the neural network, and you ask, what are the images, the input images that most activate that particular hidden unit in the middle of the code, here are the images. Here they are for a second node. Here they are for a third node. And if you backsolve, if you take that node and you ask, well, if I solve for the set of input pixels that maximally activate this node, then for this node, here's the set of input pixels that maximally activate it. And here's one. Can you actually see that? If you get the right contrast, you can see a ghostly cat. And this one. So this is the kind of thing that these networks are able to learn. Very sophisticated, very nonlinear features of the inputs. Okay, so I said that there were 2 points I wanted to make. One is, I didn't get a chance when we talked about neural networks before to point out that there's a very interesting connection between the structure of these deep networks and probabilistic graphical models, which we talked about for weeks in this course. And I think that's very exciting because it's a way, the probabilistic model perspective on this gives us a way of having a more theoretical, analytical handle on what these networks are doing. So let's talk about restricted Boltzmann machine, which is kind of the building block, the 2-stage building block of these deep networks, of many of them. And you can think of them this way. I have an input set of nodes, let's call them the vector V. I have a hidden set of nodes, let's call them the vector H. And each of these nodes in the theoretical graphical model represents a Boolean random variable. It can have a value of 0 or 1. And the continuous activation of that node represents the probability that that random variable has the value 1. So if you look at it that way, you can define the joint probability on all the nodes, vector V plus the vector E, the joint distribution, you can define as this exponential distribution, which looks vaguely like a Gaussian. This is called the Boltzmann distribution. It's some exponential to something, and Z is a normalization constant adjusted to make sure all the probability mass equals 1. But you see the thing that's actually influencing the probability are the individual V and H nodes and a weight that's learned, W sub I, J, that connects. Whoa, what happened? That connects, I guess I spent too long and it's moving me forward. So you can have a node, I guess I'm going to carry this. You can have a distribution defined in this way. So we're not going to have enough time in 10 minutes to talk about the details of this distribution and how to do the reasoning. But I just want to point out that there's a probabilistic interpretation. And if we want to train the network, we can ask our favorite question, the one we always ask. which is how do we get maximum likelihood estimates for the parameters of this network. We can write down a formula for the likelihood. We can get the derivative of that likelihood with respect to the different parameters and do a gradient descent gradient descent strategy to optimize the parameters. Now, if we're building a deep network, a common way of doing this is just to build such a restricted Boltzmann machine, and then after it's trained, put another one on top and train it. Freezing all these weights and just using these as though they were the input, building another one on top. If you do that, again, you can write down a probability distribution, which is now a joint distribution on all of those Boolean random variables, and solve for how to train it. It's complicated, but in fact, it can be done efficiently. And if you do, for example, if you train it on input characters like this, the learned probability distribution, if you have it then generate random outputs that are high probability outputs, you get things like this, which you can see is capturing much of the structure of the characters that are actually the input. If you then apply this, for example, by giving it not Sanskrit characters, but English characters, then you find that these kind of deep Boltzmann machines, once they are trained on unlabeled data, and then in the final stage, just do a simple logistic regression function on the learned internal representation, that you get the current state of the art. Why does this keep changing? You get the current state of the art results. Yeah, whatever. You get the current state of the art minimum error results on some very heavily explored data sets for character recognition, beating things like support vector machines and k-nearest neighbor by handy margin. Okay, so that's point number one. These deep networks actually have an interesting probabilistic interpretation. Some of the research that's going on today is to try to understand better different probabilistic models and the corresponding deep networks that would go with those. Point number two that I wanted to mention is, if you think from the point of view of what's the significance of these networks, to me, if you had to say it in a sentence, it's this. They learn representations, which are then valuable for many purposes. And so one of the most interesting examples of that is some very recent work that a number of groups have been doing to try to learn representations that simultaneously capture text input and associated image input. The idea is to learn an internal representation that can simultaneously encode this and encode this text string. And if you can do that, then you've learned yourself input modality independent notion representation of what the underlying concept is. So again, without going into a lot of details, we could set up a network where we have an image, pixels input, some text represented by bag of words types counts, and try to learn a shared representation. If we did that with one layer, it would work kind of not too great. But now that we have the idea of deep networks, we can instead build networks that, for a while, work on just one of the two modalities, and then at the end, try to learn a shared representation across them. And so people do this, and in fact, then they train it in a way where, given an input here, you adjust all the weights to predict this output that goes with it. And similarly, given the input here, train it so that the weights predict the output here. And if you go back to the probabilistic interpretation, what you see is that there's actually a way in which you can think of this cascade of restricted Boltzmann machines as defining a joint probability distribution on the observed pixels and text features. And it's kind of a messy looking probability distribution. We won't go into the details, but it does have components which have to do with the image processing, the text processing, and the joint third layer. So again, the point is there's a probabilistic perspective on this that we can use to then ask the question, how would we train maximum likelihood or map estimates of the parameters of this network? If you do it, here's the kind of result that you find. So here, after training, are some input images and the words generated by the trained network for those images. And I think they're amazingly impressive. Of course, these are cherry-picked. They're not all that impressive. Here's some that were cherry-picked in the opposite direction. And so you see, I put this up here to make sure you understand there's plenty of room for more research in this area. So not all cases have the right labels for the images. Okay, but you get the idea. This is something that even 5 years ago, I would not have predicted we'd be seeing. I would not have predicted in 2010 that by 2015, there would be machine learning systems that can be trained to do this kind of translation from image to text and vice versa. People use similar kinds of ideas to actually translate from English to French, and from sound to text. And I don't know if anybody's done sound to images yet, but you can see where this is headed. Okay, so maybe I'll end there and just say, so my 10 to 15 minutes that I get to use, I'm going to put forward the idea that deep networks are one of the really key developments and one that's going to help define the future of machine learning over the next 10 years. Okay, now Nina has her own idea to put forward, so I'll let her do that. And then we're going to open it up to something like a panel discussion with additional experts. So Nina, yeah. You're on. And I reassembled the microphone.
Just a second. Okay, so this is not necessarily my favorite one, just to point out, but it's something that definitely must be part of the current machine learning. It's not necessarily. I'm just talking about it because it's clearly important. I have many other favorite ones. Okay, cool. And this is really about privacy, right? As I mentioned already, I mean, right. So in some of the modern machine learning applications, we need to use sensitive data, like medical data, or web search query data, or salary data, or even student grade data. Right, so we had this discussion when we were trying to release information about midterm. We were wondering if we release certain type of information, we do release like some specific information about some of you. Okay, so it's a very important question, how to do machine learning when we deal with sensitive data, private data. Okay, and the problem is that even if the person running the learning algorithm is a trusted person, right, we can still be in a situation where the output of the algorithm really reveals some sensitive information. Okay, so we really have to be careful. So just here's an example for example, from my friend Aaron Roth, who was a student here, and now he's a world expert in privacy. So here's an example of something that could be potentially embarrassing if we are not careful. Okay. or even a more technical example. So imagine that we are doing, say, SVM or perceptron or medical data, right? And suppose that we have a feature J that is a feature whether the person has green hair or not, and assume that we've learned a W that has a non-zero weight on that feature, right? Now, if you think about how perceptron and SVM operate, this then implies that if there is only one person in town that had green hair, then we immediately know that that person was in our data set. So we could we already learned information about that person, right? So that's not necessarily desirable. Okay, so it's a question, one of the main questions now is how can we design learning algorithms that can help us avoid such situations? And I think the jury is out there. I don't think there is we don't really know exactly what is the right model and how to formalize this, but there has been some great progress in the past 10 years on a specific model of privacy, and this is called differential privacy. Okay, and there has been a lot of exciting work. And I'm going to spend the next few minutes just giving you a feel about how do you formalize privacy in the differential privacy scenario, and what can you hope to achieve. Okay, and this was actually, so the leader in this area has been Cynthia Dorr, but she has many collaborators, including Aaron Roth, who is my peer at CMU, and they actually even wrote a book about the topic. So if you're curious, you can read the whole book. Okay, good. So what is differential privacy? So the high-level idea, and you can, by the way, keep throughout, so throughout my presentation, you can keep as a running example in your head. Say we just want to do something simple, like we want to release the average grade of the course, but we want to maintain some sort of privacy, right? So this could be your example. Okay, so now here is what differential privacy would do for us. So what differential privacy would do, so first of all, instead of just outputting, so now the mechanism or the algorithm will be a randomized algorithm. It cannot be deterministic, because if it's deterministic, we can easily show it has problems. So instead, we're going to think about randomized algorithms. And so our algorithm is going to output, will basically produce a probability distribution over possible outputs, like a probability distribution over possible average scores for the midterm. Okay, so right, so the algorithm is going to produce a probability distribution over possible outputs, and then essentially the mechanism will be differentially private if it has a property that if a person I changed its input from a certain number xi to a different number xi prime, then the relative probabilities of any output did not change by too much. Okay, so imagine that this is, imagine that this was the distribution output by the mechanism if person I had as input xi, feature xi, say one feature for now. And we say that it's differentially private if our person changes its input from xi to xi prime, then basically the relative probabilities of any output did not change by too much. So in other words, these histograms look pretty much similar. Okay, so that's what differential privacy does for us. And so, okay, a bit more formally, so what differential privacy is, it's a property of a protocol A that we run on some data set in order to produce some data set X in order to produce some output A of X. Okay, and formally, and this is the formal definition here. Okay, so formally, our algorithm A is differentially private if for any two neighboring data sets that differ in just one entry, like these two neighboring data sets here, right? They're identical except for the ith entry. Okay, so what we want that for any two neighboring data sets that differ on just one entry, for all possible outcomes that the mechanism might produce, what we want is that the ratio of the probabilities of producing an outcome V, so for any possible outcome V, what we want is that the ratio of the probabilities of producing the outcome V under the first database S is close to the ratio, is basically, so that this ratio, right, sorry, we want that this ratio of producing the outcome V under the first database over the probability of producing this outcome V under the second neighboring database, so we want that this ratio is close to 1. Right? In other words, these two probabilities of producing the outcome V under the two databases are very close to each other. Okay, and formally they have this epsilon differential privacy, the parameter epsilon, and they want it that this ratio is in between e to the minus epsilon and e to the epsilon. Why did they do so? Because, I mean, this is approximately 1 minus epsilon. and approximately 1 plus epsilon, and epsilon is small, and they put it in this specific form because they want to get some composition results. So it's just for technical reasons. Okay, but this is the definition you normally see, but all it says is that for all possible outcomes, the ratio for every possible outcome V, the ratio of producing V on S over the probability of producing V on S prime is close to 1. And now here the probability is over the randomization in our mechanism A. So the mechanism A, as I said, has to be randomized, will be randomized. Okay, and I guess the way they describe this, and I wrote this on my slides, so you can think about this as being a model of plausible deniability, which just basically means that if your real input is, say, xi, and you'd like to pretend that your input was a different input, then somebody looking at the output of the algorithm cannot tell that you are doing that. Okay, so they cannot really tell if you are in the database or not. So which could be a desirable feature. Okay, so this is the sense in which differential privacy preserves privacy. It kind of gives, I mean, you have no incentive not to participate in the study, pretty much. Okay, so that's the notion of privacy. Any questions about that? Okay, good. So anyway, that's, yeah?
So is it the sense like we encode it?
Say it again?
Like we make a code or like we change the...
How do we achieve privacy? This is your question right now.
Yeah.
How do we achieve it? Okay, so that's an excellent question. Let me just mention that so far I only talked about I want to be private, and actually my next slide points this out. I mean, can we achieve privacy? And the answer is, if all I care about is privacy, there is a trivial way to achieve it. You know, just output something just output 0. Output something, yeah. Okay, so it's trivial to achieve it. But if we do so, we don't achieve any utility. So really the real question is, can we achieve privacy while still having some utility? Okay, and this is when the things become exciting. Okay, and the answer is yes, actually. So surprisingly, it's yes. And there is a very common trick used now that gives us a lot of good algorithms for many databases and machine learning applications. And this is a so-called the Laplace mechanism. So it's a common trick. And the idea is, I'm going to show it here for computing the average. Okay, but it can be generalized to many other problems. Basically, the idea is to add just the right type of noise. Okay, so if I want to compute the average, what I'm going to do, I'm going to first compute the real average, and then I'm going to add appropriate noise to the answer. Okay, so basically, the idea is we can just add, right, so as I mentioned, so it turns out that we can preserve differential privacy for many of the computations that we care about, including machine learning computations. And the idea was just add some noise, right? So for example, for computing the average, what we're going to do, so right, let's assume that we have an input in the range 0 to b. B is an upper bound. For example, here will be 100 in this course, right? And so what we're going to do, we're going to add some noise, some specific type of noise called Laplace noise that has a specific distribution. And the amount of noise that we add depends on the sensitivity of our query. Okay, so for example, when we compute the average, any single input can affect the average by b over n. And so what we're going to do, we're going to add some amount of noise that depends on this sensitivity. So in particular, we're going to add, we're going to draw x at random from this Laplace distribution that looks like e to the minus absolute value of x, epsilon times epsilon over sensitivity, which in this case is b over n. So we just draw a point at random from the distribution and add to our real average and just release that. Okay? And then you can show that this is differentially private. And how do you show that? You just use some properties of this Laplace distribution. Okay? So that's pretty much a common trick. Right, so basically, if we do so, right, exactly, if we add this type of noise, then we can prove that changing any one input changes the probability of any given answer by at most epsilon. Okay? And so that's pretty much one way to release the average while maintaining the differential privacy. And then you cannot tell whether an individual is point or not in the input set of data. Okay, and this is right. And actually, so right, then you have to go ahead and think about it. Okay, I'm not going to go for these computations, but the way to think about it, I'm going to add a certain amount of noise, and then I might ask, well, now how many samples do I need to be to then be epsilon differential private and to achieve an overall error of plus minus gamma, right? So we also want to be accurate, so we want to have some utility, and we also want to be, so maybe my utility here is gamma. I want to output something that is within plus minus gamma of the true average. right? And then I also want to preserve epsilon differential privacy. How many samples do I need? And if we go for computation, we can argue that in this specific case, we're going to need B over gamma times epsilon sample, where B is the range of the query, and epsilon is the differential privacy parameter, and gamma is the desired utility. Okay? And then it turns out that, so this is for one query. Now it turns out that this differential privacy has some composability properties. If I then want to ask k queries, then the number of examples I'll need increases by a factor of k. Okay, so that's so we can handle many more queries, like because if we do a real machine learning application, like say try to run the ID-free algorithm for learning decision trees, right? Obviously, we're going to need to compute many of these queries, right? To compute to see how good a split it is, right? So, and the point is that we can ensure differential privacy, but then the number of samples we need depends on how many splits we need to use. Okay. Right, so this is my next example. So now we can basically use this trick to then just run the ID-free algorithm. We can make the decision tree algorithm differentially private. And in general, actually, most of the algorithms in machine learning can be made differentially private. And I'm not going to go through details here, but wanted to think about it. It turns out that many of the machine learning algorithms that we've been talking about can be implemented so that they only operate with the data via statistics. Okay, and actually Michael Kearns formalized this. So he introduced a so-called statistical query model back in '93, and you can then formally prove that any algorithm that can be implemented by using statistical queries, then it can be made differentially private. And you can give a precise bounds on how many samples you need to then be differentially private and achieve good accuracy. Okay, so there is a whole very general technique here that can help us design differential private algorithms. And this is for supervised learning. You can make them active, you can make them distributed, you can make them semi-supervised, you can talk about clustering being differentially private, and people have looked at all these topics. Okay? Any questions at this point? Or comments? Yeah?
So, what kind of algorithms are like more suited to this? Because like, if there are algorithms which are noise, like they are not tolerant to noise, they will fail at this. So like, are there any specific algorithms that are useful in this case and not?
This is exactly what I'm saying. So, for example, there is a formalization called statistical query algorithms that make decisions based on statistics, based on averages. Okay, so many of the machine learning algorithms can be simulated this way. So, for example, the perceptron algorithm itself, the way I describe it in class, depends on specific examples. But I can modify it so that rather than updating the current hypothesis based on just one example, I can update it based on a sequence of examples, and I take the average of those. So you can modify many of the algorithms that we've been talking about to operate based on averages without really losing a lot of the utility, so without losing their properties. So then pretty much we're in a good shape overall. Now, if you want, there are theoretical examples. There's something called learning parity functions, where if you solve a systems of linear inequalities over Z2 or something, then that we don't know how to make the differentially private. So there are some algorithms that are not necessarily differentially private easily, but for most of the machine learning applications that we care about, I think they can be made differentially private. And this model, SQ learning model, captures that. Actually, so yeah, I mean, even my answer was a formal answer. So the only class that is known to be learnable is statistical query model, but not in with a small number of, right, the only class that is not, no, the only class that is known to be learnable in the statistical learning theory model or in the PAC model with a small number of samples, but not learnable in the statistical query model is actually the class of parity functions. So there is one theoretical example. But most of the other ones are just known to be implementable by a statistical query. So we're in a good shape. So with modifications, not necessarily the original algorithm, but you can modify them. Yeah?
Do we have any understanding of how much accuracy you have to give up to get privacy?
Yeah, so that's
Like
a trade-off.
Yeah.
All right. So,
Like, is there like a bound on how good you can do?
oh, people have results, but I mean not tight results. So, right, so for example, here, even in this simple example, I'm saying if you want to achieve accuracy gamma plus minus gamma, okay, I guess the way I said it here is if I want accuracy plus minus gamma, and if I want epsilon differential privacy, how many samples do I need, right? But then you can also ask the question, if I have a fixed sample, and if I want to achieve a certain accuracy and certain privacy, then you'd have to solve for this. So, but there is not a super tight characterization. Like for sample complexity modular differential privacy, we really know the kind of almost up to log factors, we really know what's going on. Right? Once you have privacy, people know up to polynomials, but they don't know exactly. But I think really the main question is, okay, first of all, this has been a really good direction and it's awesome, but now there is formalization. We know that we can achieve some sort of privacy and it's great. But the real question is this the right notion of privacy? And I think here the jury's out there, right? Because, yeah, we achieve just one type of privacy. There could be many, many other types of privacy you could care about, right? Okay, cool.